Okay, now we're going to the section of the design steps for the Spur gears. So the overall design objective for the Spur gears is that they should be compact and small because the size is actually going to be related to the mass as well. So we're usually looking for a more lighter machine and more less size. Also, it should be operate smoothly and quietly. And you remember that the Spur gears, one of the disadvantages is the high noise generated at the high speeds. The long life, because we want the gears to be lasting longer. The low cost, and this is another factor need to be considered. Easy to manufacture, and finally to be compatible with the other elements in the machine. So the procedure for designing a safe and long-lasting gear drive has been presented to you as steps, pointed steps. So we start first from the design requirement. We need to identify the input speed of the pinion or the number of the RPM we have for the pinion and the desired output speed for the gear. Also, we need to know what will be the power to be transmitted. Step number 2 is to choose the type of the material for the gears, such as you're selecting the steel, the cast iron, or the bronze. Step number 3 is considering the type of the driver and the driven machine, and then specify the overload factor using the table 9.1. So the primary concern is going to be the expected level of the shock or the impact loading. As we know what the value for the KO or the overload factor, now we can calculate the design power, which is going to be more than the actual power. So the design power in step number 4 is going to be equal to the overload factor KO multiplied by the power to be transmitted. And now we need to specify the trial value for the diametral pitch value, which is the PD, and this we can find it for the steel using the figure 911. Note that the diametral pitch value must be a standard size, and that's what we can see in the table A2. So the value for the PD should be one of the figures has been listed in the table A2. These are the standard one, unless, as we mentioned earlier, that you may need to make a costume gear, and this will cost you more, of course. So we have to know that as the PD value going to be decreases, the tool size will increases, and thus will bringing down the value for the ST and the SC. As the PD increases, the number of the teeth is going to be increases, and thus the gear train runs smoother and quieter, and the drive gets smaller as well. Step number 6, we need to specify the MP, the NG, which is number of the teeth for the pinion, number of the teeth for the gear, to meet the VR requirement. Calculate the center distance, D, and the OD, to make sure that there are not going to be any interference issues between the gear's teeth. Step number 7, specify the spade width within the following recommended range for the general machine drive gears. Has been described earlier that the face width should be more than A divided by the PD and less than 16 divided by the PD. Usually nominal value is going to be the average, or the midpoint, which is 12 divided by the PD. You can choose the 12 divided by the PD, and then you can modify this figure as you are going to do your second iteration if required. Step number 8, we need to remember increasing the face width will reduce the ST value and the SC value, which is very important. We're going to reduce the stresses. But we have to consider that the alignment factor should be included. The face width normally is going to be less than 2 multiplied by the DP. Okay, so now we have two ways to find the value for the F, and we can see that for the first one, the face width should be within the range of the 8 divided by the PD from the step number 1 and less than the 16 divided by the PD. But in most cases, it should be less than the 2 multiplied by the dB value. Step number 9, we can compute the transmitted load, or the WT, the pitch line speed, the VT, the quality number, the QV, and the other factors required to calculating the bending stress and the contact stress. Now we can calculate the ST and the required SAT value, and we dose the material in the 2 should meet this value for the SAT should be checked. If not, then simply going to select a new material and define new geometry, and this can be done by repeating the iteration back to the step number 4. If yes, simply just go to the next step. The step number 11, calculate the SC and the required SAC, and if the material in 2 going to meet the SAC, if not, then select a new material, and to meet the SC and the SAC, define a new geometry back to step number 4. If yes, simply continue to 12. Step number 12 is summarize the design outcome. So the table 913 is can be used by yourself to do the summary for design, and those are terms used for the gear design. So you can see that first thing is going to be the recommended quality number, or the AV. We need to specify the value for the AV, and this can be done by using the table 9.5. Step number 2 is the allowable bending stress number. For the steel, for example, we find the SAT, and this can be done by using the figure 918 in the mode book. The allowable contact stress number for the steel, and this can be found by the figure 919. The allowable stress for the case hardened steel, and the symbol for that is going to be the SAT or the SAC, and this will be, of course, is going to be for the we need to subscribe the material first and then use the table 99. The allowable stress for the non-ferrous material, and this can be done by using the table 910. The geometry factors for the bending stresses, the JP and the JJ, and this can be found by the figure 910. The overload factor, the size factor, the alignment factor, which is the KM, and the proportion factor, the mesh alignment factor, the rim thickness factor, and the dynamic factor, the equations for the KV, and you can see that it's going to be done by using the table 9.1, 9.2, the equation 9.17, the figure 9.12, the figure 9.13, the figure 9.14, and the figure 9.16. The equation for the KV is going to be from the table 9.6. The elastic coefficient CP from table 9.7, as you remember. The geometry factor for the contact stress I is going to be from the figure 9.17. The reliability factor KR is going to be from the table 9.11. The recommended life in hours is going to be from the table 9.12. The bending stress cycle factor is going to be from the figure 9.21. The contact stress cycle factor, Zn, is going to be from the figure 9.22. And the design pitch selection aid, and this is going to be from the figure 9.11. So as you can see here, the primary equation used in the gear design is going to be for the ST, the equation 916. For the required allowable bending stress number, it's going to be the equation 928, sorry. The contact stress number is going to be from the equation 923. And finally, the required allowable contact stress number is going to be from the equation 931. So we need to prepare all these parameters first, then we are going to use these equations to find the outcome of our gears. And of course, this will be by following the steps 1 to 12 and find if our design is going to be within the requirements of the design. In this week, we are going to have a quite straightforward design example for the Spur gear. We have a gear pair is to be a part of the drive for a milling machine that's requiring a 20 horsepower with the pinion speed at 550 RPM, and the gear speed is going to be anything between 180 to 190. So we have a range. So by summarizing that, we are going to find the given parameters. So we've been given the driven is going to be a milling machine, okay, and the power 20 horsepower. The pinion speed is 550 RPM. The output speed, the range of 180 to 190. So we can take 185 as the average. The continuous use for 30,000 hours, and that's what we got actually from the recommended design life from table 9.12. For the electrical motors, industrial blowers, the general industrial machines, the life is going to be anything between 20 to 30,000, so we take the maximum design life. What we need to find is going to be the compact gear design. I would like you to try to have an attempt for that, following the steps that have been given to you in this video. Then we are going to check the solution step by step in the classroom. And also at the same time, we try to build an Excel sheet for the solution. So the next video is going to be about the helical gears and their design and procedure.